Hey guys, welcome back to class. Welcome back to my classroom. We're gonna study graph theory, ACSL graph theory. You're gonna need this sheet, which you should have an electronic version of it if I send it to you. And you'll also need, this should be part of that. These two sample problems are the ones I'm gonna work out for you, but before we do that, graph theory, I'm not going to have as much time as I really need on this video, so I may have to make a follow-up video on it or something, but for now, I think I'm going to skip the part where I try to sell you on why graph theory is important. We'll save that for later, I guess, but one thing we're going to start with is graph theory has a lot of vocabulary, like what's a graph, okay? Well, you can look at the sheet. The sheet tells you that the graph is a collection of vertices and edges, okay? Well, what's a vertex and what's an edge? We'll get to that, okay? Let's just draw a graph like what's on here. If you look at the graph that's on here, well, technically, that's a graph. Actually, I could just draw one vertex, and that actually fits the definition of a graph. But we're going to be doing some things with simple graph theory here, and let me just encourage you to read the form, but I want to go through a few definitions, okay? First of all, a graph could be a connected or a disconnected graph. I like to say that if you can pick up the graph by one vertex and shake it and it doesn't fall apart, then it's connected. But if it falls apart, then the graph is disconnected, okay? That's just one way of looking at it. On the sheet there, you have two different versions of the same graph. It looks like 6 graphs, but it's just 2 copies of the same graph. It is a disconnected graph. Another characteristic of this graph on this sheet is, I'll show it to you in case you're actually watching this video without the sheet, is that this is an undirected graph. There are no arrowheads on the graph. Unlike this graph where you see lots of arrowheads, that is a directed graph, or a digraph, DI for short. Okay. With the directed graph, with the undirected graph, we can traverse the edges in any direction. In other words, I can go from A to B, from B to A to B, B to A, whatever. Okay. If I have another edge in here, I can go. This was a disconnected graph because C wasn't part of it. Now it is connected. And anyway, we can go from A to B, B to C, C to B, B to A. Okay, undirected graph, right? Those are edges. I have 2 edges and 3 vertices in that simple graph. A path from a vertex X to Y in a graph is a list of vertices. We could list a path from A to B. There's a path from A to C that goes through B. There's a path from, so we got a path A, B. We've got a path B, C. Those are edges too, by the way, individual edges. But there's also a path A, B, C, and a path C, B, A. There is no path that leads directly from C to A, okay? There's no AC, there's no BAC in this particular graph, right? It's an undirected graph. We can traverse the edges that are there in either direction and we got a limited number of paths there, okay? Actually, we don't. That was kind of a lie. There's an infinite number of paths here because there's also the path A, B, C, B, A. Okay. In fact, most of these graphs, undirected graphs, are going to have an infinite number of paths. We can just keep going. Anyway, so path. A simple path. Already part of your definitions here. A simple path. Let's read it. A simple path is a path with no vertex repeated. Okay. So, is it simple to go from A to B? There's no repetition of those vertices. That's a simple path. Is it a simple path to go from A to C? Well, there's no repetition, but the edge doesn't exist. So no, that would not be a simple path. But it would be a simple path to go from A to B to C. So this is simple, simple. It exists and it's simple. CBA is simple. But A, B, C, B, A, not simple. Okay. As soon as we backtracked from C to B, that was a repetition of B. And then when we went to A, that was a repetition of A. So it's a path. It's a valid path. It's valid for this graph, but it is not a simple path, because a simple path will never use a vertex more than once. So you might have an infinite number of paths, but you're only going to have a finite number of simple paths. And then there's the definition of a cycle. Now, a cycle is a little bit tricky, okay? ABA is a cycle, because a cycle will return to the vertex that it started from, okay? The path, a cycle will be a path, but now, of course, not all paths are cycles, but the cycle will go from wherever it starts, it'll return back to it without any repetition in between, okay? So ABA is a cycle. And here's the funny thing. BAB for this graph is the same cycle. That's the tricky part. Okay, we'll look at the definition on the sheet in a second. But ABA are distinct paths. They are not the same path. But by definition of cycles, they are the same cycle. Okay, we can add something else in here. Make it a little bit longer. We'll do that in a little bit. But I just wanted to read the cycle definition with you. A cycle is a path which is simple, or would be simple, except for the fact that the first and last vertices repeat. Okay, so it returns to wherever it started. It starts at A. It returns to A. Oops. A, B, A. Okay. B, A, B. Same cycle, but different paths. I guess I didn't finish that definition, did I? The path AFEGA in this graph that we're looking at, the path where'd it go? AFG, I lost it, totally lost it. There it is a cycle in our example. Vertices must be listed in the order that they are traveled to make the path. Any of the vertices may be listed first, and that's the trick right there. Any of the vertices may be listed first. Okay, so FEGAF is a cycle, and GAFEG is a cycle, but they're the same cycle. They're just different paths. Okay, so you might want to think about that for a little bit. All right. Digraphs, directed graphs, are the ones that have the arrowheads. Okay, and if it has an arrowhead, you can only traverse it in that direction. Okay, so it's a bit more limited, and we'll look at some of that in a minute. Now there's some other definitions on here I need to go over with you, but I just need to do it. Okay, so there's this sheet here. It has two graph theory problems on it that we're going to work out together. And the first problem is asking us to find different cycles in a graph. Now, you can find graphs and cycles by inspection, by just looking and finding them. But it's not a very systematic way of doing it. Okay, you can easily overlook some of the cycles there, or maybe repeat them, and you don't want to do that. So in this first problem, first we're going to draw the graph that's specified, and then we're going to find the different cycles that exist in that graph. And I'm going to show you a special way that a young lady named Emily, way back in, 2008, said, hey, we were stuck. We were like, we need to be able to find cycles. We need a systematic way of finding cycles. And she came up with it. I'm sure she didn't invent it, but she thought of it before I did. And so I always credit her for that. And anyway, we're gonna do that. We're gonna have a systematic way where we can know we've gotten every cycle and that there's no redundant cycles in there. These are redundant cycles. ABA and BAB are redundant cycles. because even though they're different paths, they're the same cycle. And whenever we're listing cycles, trying to find a number of cycles, counting cycles, we don't want to count a cycle more than once, okay? So this would be one cycle, not two. All right, so we're going to do that. On the second problem, what we're going to do is it's asking for paths of a certain length. Now remember, paths in general could be infinite, even in a directed graph sometimes. But when you're trying to find paths in general, it has to be a certain length. Okay, paths of length 2, paths of length 3, paths of length 4. Usually we won't go any further than that most of the time. But usually paths of length 2, 3, or 4. And what we're going to do is use a technique from second-year algebra, matrix multiplication. Hopefully that'll ring a bell for some of you. Matrix multiplication, it gives us a really good way to know where the paths of a given length start and end and how many there are. And given that information, we have better than just inspection to go in and try and find them, because we know where they start, we know where they end, we know how many of them there are in those positions. And that's what matrix multiplication will help us with. So I'll do that too. And like I said, I got a kind of time limited on this video, so I'm kind of rushing through more than I usually would.